Okay, so yeah, I'm Sean Kroll. I work with Elizabeth on her master's work. Her advisor Feng Chu is here in the room. You can't see him, but he is here, I promise. So we're all official. But Elizabeth came to OU in 2020. Was it?
Honestly, 2021. Okay, yeah.
It was 2021.
The years have gone by.
Yes, the years have gone by, but that hasn't been that long, honestly. Less than 2 years if you think about it. So, and I've been really impressed coming from Virginia as an engineer to see Elizabeth spin up so quickly on meteorological concepts and all the stuff that she's learned. She planned a field campaign, not the whole tracer campaign, but the GeoCarb-TRACER part of the tracer campaign. Planned it, executed it with some help. Oh, there's Petra. And has now spent a lot of time analyzing the data, making sense of things. And this is her seminar on the defense will come in the summer. So this is just sort of a snapshot of where we are with research, but I want to say that this has been kind of a very fast-paced master's degree, but you've done really, really well. Yeah, I think that's all for now.
All right. So, yeah. Thank you, Sean. All right, cool. So thank you all so much for being here today. Really do appreciate it, everyone here and online. So, without further ado, let's just jump into it. So as Sean mentioned, this past summer, I led a field campaign in Houston, Texas called the GeoCarb-TRACER Campaign. It was a part of the greater DOE ARM Tracer Campaign, which, as you can tell by the full acronym, they were very interested in aerosols, convection, and their interactions. We, with the GeoCarb-TRACER Campaign, were focused on something slightly different. We really wanted to look at the greenhouse gases that were produced in this highly urbanized and industrialized environment that is the greater Houston area. And we did this using EM27 spectrometers, 2 of which you can see in the main picture on the right. So what exactly is an EM27? So an EM27 sun is a Fourier transform infrared spectrometer that is produced by Bruker. Essentially what it does is it measures the near infrared downwelling radiation from the sun, giving us data as you can see on the right. So picture an Earth with no atmosphere. Essentially, this plot looks like a very nice smooth curve because we are seeing all of the radiation that the sun gives off. But instead, we have stuff in our atmosphere, and each of those constituents absorbs solar radiation at a different wavelength range, depending on its chemical characteristics as well as some of its physical characteristics. So we look at this wide range of downwelling radiation in order to pluck out information about primary greenhouse gases, such as methane and carbon dioxide, as well as greenhouse gas water vapor, as well as carbon monoxide. So we end up getting this information by putting this raw data into a retrieval algorithm. The one that we use is designed specifically for use with EM27s called ProFast. And we get out these total column dry air mole fractions. So with the equation on the right, we calculate these mole fractions by looking at the column abundance of a gas, dividing it by the column abundance of oxygen, and then multiplying that by the fraction of dry air that is oxygen, hence the total column dry air mole fraction. So I'll commonly refer to these as total column concentrations, as it's just a tad easier to say. The other thing that the EM27 gives us is a value called X air. So it'd be a little bit difficult to determine the total column dry air mole fraction of air using this equation. So instead, this value is calculated as the surface pressure divided by the measured column of air, meaning it should be 1 throughout the day, or at least very close to it. And so it allows us a great look into how the EM27 is operating. If we deviate from that, we know that something has gone wrong, and we can adjust our data approach as such. So if we're in the field, we take out our EM27 sun, and it's a bit of a wordy name, so I like to call ours Blanche from the Golden Girls. So the external optics of the EM27, if you haven't seen it, are gold, and so it makes sense that the name is as such. So we take Blanche out on a nice sunny day, we set her up so that she can see the sun. We align the optics so that sunlight is filtered into the box where we have more internal optics and our sensors. That way, if we are deploying near, say, an industrial site or something else that will produce the greenhouse gases we're interested in. If they are emitting, we can potentially get some of the data like we saw on the previous slide, which then we can run through the retrieval algorithms and get out our total column concentrations. So that's this data in a nutshell. So during the Tracer campaign, we took Blanche and a couple of her friends, graciously lent to us by a couple of organizations, to Houston for a total of 64 daily data sets. So between the 4 sites that we deployed at, we had sites 7 and 8, both hosted by the University of Houston, very graciously. These served as more of our urban sites. We had site 6 at the Coastal Center, which as far as tracer sites go, this was about as much of a background site as you could get without literally being on a boat. So it was best for us. And then we also had site 5, which could act more as an urban or a background site, depending on the wind resource. For the purpose of this presentation today, I'm going to be focusing on site 7, which is our UH main site, which is located very near or very close to downtown Houston. So at this site in particular, Blanche was able to collect 19 daily data sets. We were co-located at this site along with the University of Houston's launch trailer. So they launched a lot of radiosondes there, as the name implies. But there was also a celiometer, a Pandora spectrometer, and other instruments. While we think that there is a lot of interesting analysis that we can do in the future related to these instruments, the ones that I'm going to be focusing on today are the basic ones. So just the surface meteorological data, so specifically temperature, relative humidity, pressure, wind speed, and wind direction, as well as the data that we got from Blanche. So once we have collected all of the data, the first thing that we need to do before diving straight into the analysis is quality filtering the data. This is obviously going to be very important to make sure that we're not analyzing anything that was created by the instrument. We want our analysis to be representative of the atmosphere. So the first thing that I do is remove any unrealistic values, like concentrations of 0. They simply don't exist. Additionally, this step is grown slightly, so that X-air value that I mentioned earlier, if we noticed an excursion in X-air that was not physical, it was due to the instrument. There's been some manual trimming of the data. This only happened a couple of times, and in the future will be replaced by a more deterministic approach, as opposed to a subjective one. Additionally, I like to filter the data by solar zenith angle. So that means that with a bound of 75 degrees essentially means that any data collected very early in the morning or very late in the evening, we're just going to set that aside for now. And finally, for XAR, we want to make sure, since it is supposed to be a value of 1 throughout the day, that it is pretty close to that value. So we have a filtering step for that as well. So once we have filtered our data, the big question that we want to ask, and the question that I'll be addressing today, is can we contextualize our data using indicators of boundary layer processes? So the boundary layer is a big part of transport uncertainty, and we want to find out ultimately why, we see big excursions like this, for example, in XCO2, where our concentrations on a single day were much greater than the mean, sometimes even greater than a single standard deviation away from the mean that we had been seeing at that site. Can we contextualize that with what we see at the surface, what we know about the boundary layer? Ultimately, all of this can lead into the second question, which will become essentially more of a future work of this project. Can we apply this boundary layer information to identify local sources and sinks of trace gases, which for a very urban and industrialized environment with a bunch of complications related to zoning laws is something that a lot of groups are very interested in. So let's go back to our UH main site. So here you will see all of the filtered data that we were able to collect using Blanche the M27 at this site. On the left are all of the time series, and on the right you see the same data just plotted as a function of wind direction. So all 19 days are represented here, just 2 representations of them. As you can see, each one of the days looks to be fairly unique. However, there are some trends that start to pop out as you just look at the data. But most notably, and the thing that I feel like is most important to get from this raw data is the fact that there is actually a seasonality of CO2 that we're seeing here. So the plot that I have on the right is actually taken from the Mauna Loa site. So the Mauna Loa site, if you're not familiar, it's a very historical site, honestly, in measuring CO2. And the values that we see at this site aren't representative of the carbon dioxide values that are seen anywhere in the Northern Hemisphere. However, the trends that are noted here are known to be reflected in the CO2 seasonally in the entire Northern Hemisphere due to the cycles of plant respiration and photosynthesis. So because we have the seasons the way we do in the Northern Hemisphere, and because of the existence of plants, we simply see this trend. And we find that it is reflected in our data. So in June, we had the highest concentrations that we had seen of the campaign, and by September, we saw the lowest. So this nicely reflects the global or the Northern Hemisphere trend that we would expect to see, and suggests that we didn't have any pollution events that greatly skewed this general trend. We stick by it for the most part, which is good to know on a seasonal cycle. However, it's important also to analyze things that are happening at a smaller temporal timescale, which is what the majority of the rest of this analysis is going to be focusing on. Because as you could see from the previous slide, there is a lot of data, and a lot of it looks very different as you go from each day to day. So the way that I went about this analysis of these smaller temporal timescales was using clustering analysis. So if you're not familiar, cluster analysis is essentially an unsupervised machine learning technique, meaning that we don't have a target variable that we're trying to predict. Instead, we're trying to see what relationships lie within the data. We're trying to figure out the structures that lie in the data that might be a little bit difficult to understand by just looking at the raw data itself. So take, for example, this point cloud. At first glance, you might not see a lot, but if I were to give you a marker and say circle where you think that there are higher points, you might come across something like this. And that's exactly what clustering algorithms will do, each in their own individual way. So the pros to cluster analysis is, first off, they're generally robust to outliers and noise. And as you can tell, they're pretty great at visualizing things. This also allows for us to take a more holistic analysis approach, as opposed to trying to focus on small subsets of the data to understand the trends that are going on during the campaign, which is one of the big reasons that I wanted to use it for this analysis. As far as cons go, the methods are a bit subjective. So users have to choose hyperparameters, and those hyperparameters aren't really trivial to choose. So it's just sort of the nature of the beast that if you run a clustering analysis and you don't like the results, you change them. You look at a different method, you tune the hyperparameters, but this is simply a great way of giving us a qualitative idea of what the data are showing. So then you can take that information and then apply a more quantitative approach so you know exactly what's going on, the specifics, the math. So the algorithm of choice that I will be discussing with you all today is called dbScan, or density-based spatial clustering of applications with noise. And so this algorithm will take a data set that looks like this. It's quite complex, you see, but there's some nice patterns that show up in it, and it will directly group them into clusters, exactly as you would expect. And the reason that this is important, we've got a very similar graphic to the previous slide, is that traditional means of clustering analysis will tend to group the clusters in more sphere shapes or more circle shapes for a two-dimensional representation. Whereas dbScan is a little bit more complex and allows for these different trends, these less spherical trends to sort of pop out within the data. And as the name implies, it's also great with noise. So the two hyperparameters that are used to tune this analysis are EPS, which is the radius of what we call the epsilon neighborhood, which is essentially your ideal neighborhood cluster. So for a point to be in a cluster, the density around the point must exceed some threshold, and that threshold is set by our min points. So essentially, we're looking for clusters of dense amounts of data with center points and with border points. And that's how dbScan is able to say, this is one cluster, and these are some other clusters. So in order to properly prepare the data for dbScan, we need to standardize it. So standardizing the data prior to cluster analysis is a very popular technique because clustering techniques are typically very scale sensitive. And so I've gone about this using z-score standardization for the full data set. Full data set meaning all of our surface meteorological data, all of our X-gas information, as well as 2-minute rates of change of our X-gases, and a couple of pieces of information about time, so literally time of day measured in seconds since midnight, as well as solar zenith angle. And this is a pretty simple process. Most of us have heard of a z-score standardization. However, it's worth noting that for wind speed and wind direction, we have to look at the U and V wind components in order to properly get our wind speed and wind direction means and standard deviations. So that's all the equations that you see on the right is associated with that process. So once we've standardized the data, we throw it into our DBScan algorithm. What do we see? Not a whole lot at a cursory glance. So before I get into what this plot really tells us, I will point out that, as I mentioned on the previous slide, the data were standardized before going into this clustering algorithm. However, I've gone to the effort of making sure that the X and Y axes are representative of the unscaled data. That way you can get a good idea of what is actually being plotted. So the red markers on both the X and Y axes are representative of the mean, and then the point to the right or above it is going to be +1 standard deviation. I think you get the picture. So when we analyze the entire data set, all of the data I mentioned on the previous slide, we see that DBScan only wants to put it in a single cluster. It doesn't provide us any useful information. So the next thing that I wanted to try, because obviously this doesn't give us a whole lot to go off of, is let's just simplify the problem. Let's look at an ideal transport representation. How do our X-gas variables and our wind resource information, simply our wind direction and our wind speed, what do they tell us about the full picture of what's going on? So if you only use this information within the DBScan, you see that we actually get 6 clusters out, which is much better than 1. However, you can see that some of the clusters, specifically around, let's see, 115.2 in XCO2, there are multiple clusters occupying about the same space. So that means that these are describing very similar characteristics. Additionally, cluster 1 contains a majority of the data still. So to me, this means that there are relationships that are not explained fully by this representation. So since I threw out everything other than our X-gas concentrations, our wind speed, and our wind direction, the next thing that I did was to look and see what our other surface met data, our pressure, temperature, and relative humidity, were actually telling us. And this introduces a ton of variability when we run it through DBScan. The daily structure is mimicked, but instead of just 19 clusters as we would represent our 19 days, we have 33. So DBScan is trying to pick up on things in such a way that it's a tad questionable, honestly. So it's obvious from these results, or at least to me, these were the conclusions that I came up with, that wind direction and wind speed are going to be very useful in clustering the data. Obviously, we have local transport that is happening. We know that from a physical standpoint. But this information alone is not sufficient to fully describe all the relationships. Instead, we need to look at some of the other things, whether it be temperature, pressure, and relative humidity, or other sources of data to fully understand what is happening during the campaign. And one way that we can do this is by using a more powerful tool. We need a bigger hammer. So this hammer that I decided to use is called UMAP, which is Uniform Manifold Approximation Projection. So this is a pretty robust dimension reduction technique. So if you've heard of principal component analysis, or PCA, it's very similar to that, except this technique is based in topology. So as such, I will be using it simply as an application, like many other scientists in the field, and I will not be fully explaining the math to you here today, or else it would be way more than a single talk. So the way that this works is essentially by taking an object. So like I've got this coffee mug here. It can be essentially modeled as a manifold. We can say this is a manifold, sure. So we've got this mug, it's got Shakespearean insults on it. The background is white. It is, topologists are most interested in the number of holes, so we've got 1 hole through it. We can take this, represent it as a manifold, run it through the algorithm. So for my dimensional reduction technique, I use my scanner, and we can get a 2D representation, for example, of what this mug or what this manifold representation actually is. So we lose a little bit of the understanding, but we still see there's still 1 hole there. We still see some of the insults. Some of them are a little blurred out. But we've kept the majority of the information of the data, but representing it on a more simple space. So essentially, in order to run this algorithm, we're going to put all of the data that we think are related to our feature of interest into the algorithm. So all of this other data is notated as the state vector space, and the feature of interest is what we're going to withhold from this. So the data set is still the same as I've shown previously, but I'm going to be focusing today on simply the results for XCO2. So that is going to be our feature of interest, and it is not used in order to cluster or in order to reduce the dimension of the data. And this is due to something that's commonly referred to as information leakage. So basically, if you have any direct information about a variable that you're focusing on, then machine learning techniques will like to focus on it. It won't give you the most valuable information about everything else in the data set. So that's why it is withheld. Additionally, I would like to point out that I'm only going to be analyzing the surface meteorological part of the state vector space. And so any co-emission analysis will come in later analyses. So when we use UMAP, we ultimately get out a couple of vectors. That was by design. I wanted a simple representation of the data, so I told it to only give me 2 dimensions of the data. So all of the points you see here are the 2-dimensional summary, if you will, of the data. And it is colored by temperature. Similarly to before, scaled values went into this analysis. However, I've adapted the color bar so it actually represents the physical values. So when we look at the coloring of temperature for these 2 vectors, we can point out areas of higher and lower temperature. And we can do the same thing with other elements of our state vector space. For example, pressure. And the things that I'm focusing on here for these more simple variables are regions of this 2D representation where we have values of our shaded area that are at least 1 standard deviation above or below the mean. So we can do the same thing for relative humidity. Wind direction gets a little bit more complicated. I've grouped this based off of northeasterlies, southeasterlies, and then everything from southwesterlies to northwesterlies because they weren't that common. And as you can see, we have quite a bit of southeasterlies, which is what you would expect if you looked at a climatology of the wind resource in Houston. Wind speed, I've similarly defined specific categories for. So we've got very low wind speeds. So, if you're familiar with Beaufort scale, 0 to 1. So this is just enough to move the smoke around if you've got smoke coming from a source. And then higher wind speeds, which aren't very high at all, but it's enough to feel something on your face. So we can cluster based off, or we can group based off of that as well. And finally, we have a representation of local time, grouping specifically based off of morning and afternoon. And now I will show the vectors from our UMAP analysis colored by our feature of interest, which if you'll remember is XCO2. So just immediately looking at this, a couple of groups pop out. So there are obviously areas of higher XCO2 as well as lower XCO2. However, if you'll look closely, it seems like there are some very high XCO2 points that are hidden in the largest group that's represented by these 2 vectors. So in order to get a better look at this, I decided to increase the complexity of my UMAP representation into 3 dimensions. So as you can see, this essentially for our first and second vectors is just transforming the data. The information is essentially the same, but we have a rotation and a little bit of a reflection here showing just the data, but rearranged, if you will. So if we look at an actual 3D representation of this, we can rotate, zoom and enhance, as they say, and see that hidden in this large group of points that UMAP wants to collect most of the data in, we do have a significant cluster of these high XCO2 points. And notably, these high XCO2 points are the highest XCO2 points of this entire data set. So all of them are hidden in the 3rd dimension within this larger point cloud. So we can consider that one of our high clusters as well to analyze. So now, now we reach the point where the plots get a little painful, and I apologize, but I'll break it down for you. So here you can see the overlaps of all of our different high and low XCO2 areas, as well as our high and low areas, or at least significant areas, for everything in our state vector space. And it's quite busy, I do understand that. So let's just focus on the high XCO2 points for now. So between our 3 high XCO2 groupings, as I mentioned previously, our 3rd grouping does contain the highest XCO2 of the entire data set. And the most notable feature about this grouping is that these data were collected when there were easterly to northeasterly winds. They were also associated with low relative humidity and temperature, but the winds are the focus of the focus of the reasoning behind the high XCO2 values for the most part. Additionally, our high 1 and 2 groups were related to high pressure, low wind speed, and variable wind directions, and these were also data that were collected in the morning. So if you know much about boundary layer meteorology, you're probably already piecing everything together, but nevertheless, groups 1 and 2 are quite indicative, in my opinion, of the boundary layer evolution that you would expect to see early in the morning. Got low wind speeds, variable wind direction, as our nocturnal boundary layer is starting to be mixed out by diurnal heating that is generating our convective mixed layer during the day. All of the emissions that happened overnight were, well, first off, overnight, they were accumulating in that nocturnal boundary layer. And as the mixing is occurring throughout the morning, that is slowly getting dispersed. However, since we had that increase in concentration happening overnight, we're still seeing effects of that as we do not have a fully mixed boundary layer in the early morning. So our high 1 group was collected before 10 a.m. So this analysis lines up perfectly. But when I looked at the high 2 group, I was a little bit confused. This data range was collected through early morning into early afternoon. And so this initially was a head scratcher, but then upon finding data sets from a previous study done at a site that was very close by in the Houston area, it's worth noting that the convective boundary layer isn't fully developed sometimes until 3 o'clock in the afternoon. And so it is reasonable to say that the boundary layer is still being mixed out up into the early afternoon. So ultimately, these clusters or these areas of high CO2 seem to indicate that we have local emissions trapped in the nocturnal boundary layer, hence why we're actually seeing these signal enhancements. So let's move to group 3, our outlier for the high groups. So these data were collected when we had easterly to northeasterly winds. And what's to the east of our UH main site? The Houston Ship Channel. If you're unfamiliar, it is probably the highest density of industrial sites in the largest area in the greater Houston region. So simply because we have easterly winds predominantly for this cluster, and it is the cluster with the highest XCO2, this appears to suggest from just a basic analysis that the air that we could have been sampling was from the Houston Ship Channel. We could have been sampling these local industrial sources. We're now moving on to our low XCO2 groups. Groups 1 and 2 occurred during low winds from the southeast in the afternoon. Our low group 3 was slightly different. It occurred in the morning with winds from north to northeast. And our 4th low group did not really fall within any ranges of our state vector space. So it's, by the terms of this analysis, a little bit of a question mark. So focusing specifically on groups 1 and 2, we have once again an indicator of boundary layer meteorology showing up here. The data were collected in the afternoon. As I mentioned previously, as you have diurnal heating throughout the morning, you're going to be generating a daytime boundary layer that is much taller and much more mixed than something that you would see overnight. So the fact that we're seeing something in the afternoon makes sense that we're having lower CO2 concentrations if we aren't directly sampling a source, which also makes sense due to where the wind directions were, or where the wind was coming from. We had southeasterlies from the surface, and to the southeast of the UH main site is predominantly residential and commercial areas. So once again, we seem to have a relationship between our XCO2 values and where the, first of all, boundary layer conditions, and also where the surface air is actually coming from. Now to group 3, once again, a little bit of an outlier. So these data were collected in the morning, but we observe lowest concentrations at these times. So why exactly is this? So first off, we have slightly higher wind speeds, but as I mentioned earlier, these wind speeds aren't very high. It's not like we had a big weather system moving through that was causing us to have very high surface winds, as we might see out in the plains when a cold front goes through. But yet we still have the lowest XCO2 of the group. So one thing that I noticed is that we have northerlies to northeasterlies during this group, which once again is a more residential and commercial area. So This could be playing a role, but also potentially we could have heightened wind speeds causing enhanced mixing, which would potentially be diluting any local sources that we might be seeing. But more information is ultimately needed in order to make that conclusion. So in summary, we can clearly see that a seasonal trend using the raw data is very evident within everything that we collected at the specific site. However, UMAP very clearly tells us that the diurnal trends of XCO2 are very strong. We observed them multiple times. So the things that we're measuring with the EM27 are definitely impacted by boundary layer evolution. Additionally, wind information is very suggestive of near-surface pollutant transport, which you might expect, but first of all, using an EM27 is definitely an interesting choice for all of this because they measure total column concentrations. We're seeing everything from the surface to the top of the atmosphere. So the fact that we could potentially be seeing local enhancements is very notable. Additionally, different data, I believe, should be used in this analysis in order to fully constrain what we're seeing. So our low group 4 could not be well constrained by anything that we were looking at. And additionally, though I was noticing trends in temperature, pressure, and relative humidity, I think that these are likely indicative of meteorological conditions, including boundary passages, that we're simply not describing well by the current example of the state vector space. So if we use different data types, we can better understand what is truly going on within this data set. So now that we have our qualitative analysis of this data, the next thing that we want to do, like I alluded to earlier, is throw these UMAP vectors back into dbScan, because ideally, this clustering algorithm would identify the same high and low clusters that we were seeing. But unfortunately, initial analysis does not exactly show that. So the next steps are going to be to tune the hyperparameters, both in UMAP and in dbScan, to try to especially get that high XCO2 cluster to pop out, because that is ultimately the area that I'm most interested in. But additionally, alternative clustering techniques might be best to fully understand or fully qualitatively describe the quantitative analysis that I've shown today. But finally, once we have a good mathematical representation of all of this with a clustering algorithm, the next thing is going to be statistical analysis. So that's getting the, as I mentioned, the quantitative analysis to match the qualitative analysis. So we actually have the true math, the true understanding to match what we think that we're seeing with the trends in the data. So overall, in summary, as I mentioned previously, we definitely have a Northern Hemisphere seasonal cycle of CO2 represented within this data set. However, local sources and boundary layer processes are hugely important with what we see, especially with small scale variability, and likely are representative of the highest and the lowest concentrations that we saw during this campaign. And UMAP was sufficient in picking up on these trends. It's just a matter of finding a clustering algorithm that will work well with it. So further analysis, other than the things that I mentioned previously, are mostly to include other data sources. So we have data from the other tracer deployment sites that we're going to be able to include in this. We're also very soon going to be including boundary layer height in this analysis. And hopefully soon we'll have insight to include for sea, bay, and land breeze information, so we can better understand what the boundary layer was doing and not simply have to make assumptions and guesses as to what was happening during data collection. And finally, I think it would also be very interesting to use land use data. So if we provided the algorithms with an idea of where the industry are, where the residential areas are, do these algorithms actually draw out the same conclusions that I see when just looking at what the current representations show. And finally, all of this to say that this analysis could lead to some pretty interesting projects related to machine learning in the future. If we can fully understand how EM27 data is related to what is happening near the surface and in the boundary layer, we can potentially use this in order to predict concentrations of trace gases based off of what we see around us and based off of what we can measure with very simple sensors like we were doing within this analysis. Our temperature, pressure, relative humidity, wind speed, wind direction, those sensors exist everywhere. So if we could actually use that information to do some predictive analysis, we could have a very interesting tool on our hands to help us understand air quality, among other things. So With that, I would like to thank the GeoCarb mission for funding, as well as everyone here on the slides, everyone associated with the campaign, and all of you who attended this talk. I do greatly appreciate it. And at this point in time, I'll take questions.
So great talk, Elizabeth. Yeah, let's open it up for questions. Yeah, I'll let Elizabeth point in.
All right, Drew, go ahead.
So you mentioned group 4 not being, I forget the exact words you said, but like it wasn't mapped well in the vector space. I actually think that it was the origin, that your vector space was being mapped from that point onto different day qualities or whatever. So like whatever happened at below 4 is kind of the center of what would be your vector space, and then it would change going outwards away from that. Because the values for V1 and V2, they were both 0, which means it would project onto it.
Sure. Okay. No, that's a good point. So for those of you online, Drew pointed out something associated with my UMAP analysis. So going back through this, my low 4 group is actually, well, it's slightly off of the origin, but it's very close to the origin. And so the fact that it is at, the zero coordinate of the UMAP vectors could be why it was not very well represented in the state vector space. So thanks for pointing that out. That's interesting. Brad had his hand up first. Go ahead.
Just a quick question. I noticed that you said you used Z-score standardization. Did you do a PDF to prove that it was a normal distribution so that you could use these scores?
So great question, Brad. So I'm not going to go back to it because it's way too far back with all of my transitions. So, but for those of you online, Brad was asking me, since I used Z-score standardization, did I prove that I had normal distributions first before doing that? And the short answer is yes and no. So it's no, it's no, because what I did primarily was looking at the mean, the median, essentially box plots, if you will, so the quartiles of the data, in order to make sure that I didn't have major outliers that were skewing the data. However, due to the nature of some of the data, they're not going to be normally standardized exactly. They're going to be, the average is going to be shifted to one side or the other. The specific term is escaping me at the moment. However, despite the fact that the data aren't exactly going to be normally standardized or normally distributed, I will say that this simplification is commonly used despite the fact, despite if the data are normally distributed or not. So whether that is a flaw in the methodology, I'll leave that up to you. But just know that it's a common approach. It's not necessarily the fact of we're looking at a Z-score. It's just this is a way to standardize it so that higher standard deviation and higher means aren't necessarily impacting what the algorithm is showing us. If that makes sense.
I'll leave it up to funds to the statistics.
Fair enough.
So,
all right.
Thank you.
Yeah. All right, Connor.
So I've seen the mono-level plot before with like that seasonality of CO2.
Yes.
And we talk about climate a lot, but how important a change of 1 to 2 parts per million of CO2, on a monthly to yearly scale, because that plot shows seasonality, not yearly trend. Can you just speak a little bit about what difference does having 420 ppm versus 416 6 months later, what impact to climate emissions, to your research is that? Because if you look at this standardized, is that 1 standard deviation? Is that 10 standard deviations? Because I would think 1 over 420 is a very small percentile change.
Sure. So for those of you online, Connor is essentially asking how these small changes in CO2 concentrations are really having an impact on things ultimately, because, if we have small differences in our concentrations, what does that really mean in the grand scheme of things? And to that, I'd say you have a fair point. So obviously the important thing about the Mauna Loa data, the Keeling curve, is that, well, obviously we have this seasonal cycle, but it's increasing over time. So, that's the bigger picture of things, is that climate is impacted by the mean of CO2 in a seasonal cycle increasing over time. If we have small increases of CO2, for the people that are sitting around, it doesn't mean all that much necessarily. However, simply noting the fact that we are able to capture trends like this, and we are able to show a very clear gradient in the seasonality of our CO2 is indicative that the methods that we're using in order to analyze our carbon-based emissions are fairly accurate, I would think. It's also worth noting that while the focus of this presentation is on local and urban emissions, the other thing that we're doing with this data is validating space-based remote sensors, in which case, knowing that we have very accurate data is extremely important, because we use those space-based sensors to tell us about what's happening around the world. And so if we know that it's inaccurate, then we have a problem. So, yeah. Sorry, go ahead.
So you use the number of clusters in your DB scaling method. How do you determine how many clusters you will? What determines the number of clusters?
Great question. So I'm going to end the slideshow briefly, only to then re-show it, because I've got a slide at the very bottom and I don't want to, blind you all with the rapid transition. Okay. Cool, we can see that. Oh, shoot, okay, thank you. All right, so we're good now?
Yeah.
Perfect, okay. So the way that we essentially, so Sarah was asking how we determine how many clusters that we see within the dbScan algorithm. And we don't directly tell dbScan how many clusters we want to see. dbScan optimizes the number of clusters based off of the hyperparameters that we choose to input it. So as I mentioned previously, that's the radius of the epsilon neighborhood as well as the density threshold. And we can use these, or we can essentially estimate the optimal values for these using a heuristic that was determined by the creator of this algorithm, Esther, which essentially is using a k nearest neighbor's distance. So the distance from each point to the closest neighbor is calculated by the algorithm and then plotted, as you can see here on the x-axis, in order from smallest to largest distance. And so the way that we can choose our ideal epsilon neighborhood radius is by looking at where we have, the biggest change in slope here in this plot of that k nearest neighbor's distances. And so that will tell us our epsilon, and then our min points is simply, well, typically it is considered to be the dimension of the data -1.